is coming next. But before that, I think we're going to have the last presentation from Dirk Van Hoen from Vito, Belgium, about the results of testing of a smart controller for peak shaving in an Italian demo case. Dirk, the floor is yours.
Thank you, Michele. Indeed, my name still is Dirk van Hout and I still work for Vito. Last presentation brings us back to district heating. I hope I don't bother you too much with it. So this presentation are indeed results of tests we did last winter season in February and from, well, December, February of last year. As you will notice, it also reveals that real life is sometimes way harder to deal with than simulations, but we'll get to that. Smart energy systems, I already explained this morning. What you will see is way more integration of the power grids and the heat networks in future to get the entire energy system as efficient as possible. And therefore, these smart energy systems, they contain some features which make the network more reliable and more sustainable. And those features are already introduced in planning phase, design phase. But we will focus in this presentation at least on the operational phase of a district heating network. So how we at Vito look at smart control of heat networks. Well, what we do or what we try to do is in a heat network, there's a lot of flexibility available. You have the buildings itself, which contain a lot of thermal mass that you can activate, but there's also the possibility of having storages in the network, be it centralized or decentralized. And actually, the network itself contains a lot of water, so you can also use the piping network itself as a storage system. And once you use this flexibility in a good way, you can achieve, or you can manipulate the heat demand curve of the network to get a certain objective. And this can be peak shaving, for example, or interacting with the electricity market, what we saw this morning, or, for example, return temperature reduction. We've been working in a few projects. These are the larger European funded projects that we are active in. But so we've been developing what we do already for a few years. How we dealt with this network is every network has its low-level controllers. So the valves in a network has its own control. The production units have their own control. What we did was we added a hierarchical level on top of this, a supervisional control level, that will actually manipulate the set points of these low-level controllers in order to achieve the objective that we want to. So it's actually an extra control layer on top, which is based on an MPC, so model-based predictive control system. In this case, we run this MPC every 15 minutes, and it calculates an optimal control schedule for the next 24 hours. And it does this by solving an optimal control problem that you probably all know. I mean, this methodology. Of course, in the heart of the MPC, you need the models. And in this network, we use 4 models, actually. There's a model of the thermal network, which predicts the flow rates and the temperatures propagation throughout the network. And for this, we use the regression model trained by measurement data that we acquired from the network. Now we have a model for the substation, the connection between the network and the building. And actually, we modeled it as being just a heat exchanger with a heating curve and a control logic. And this model gives you the supply temperature going into the building. Then we model the space heating system, so all the radiators and things that you have inside of your building. In this case, we just modeled it as being one radiator, so it's kind of a lumped model. And this model will output the thermal power, the flow rate, and the return temperature prediction from the building. And then finally, we have an RC model from the building itself, from the building envelope, which calculates the losses to the environment, and as such also the indoor temperature evolution. So that is how we did it, and that was then applied to this case study in Italy, indeed, in Brescia, where the network in Brescia is the largest in Italy. What we did there is that we, together with EI.A, which is the network operator, we looked for a peripheral branch of the network where we could play with, let's say. And in fact, behind or this branch consists of an apartment building with, I believe, 43 apartments and 34 single family houses. Total capacity of 700 kilowatts. So it's a very small site, but at least it was used to verify what we have developed. Here you see the schematics of what we did. So you have the main heating grid, which is operated by EI.A at high temperature. So in peak winter conditions, it's, I think, a supply temperature of 130 degrees. But by installing this mixing station, what you can do then is you can reduce the supply temperature going into the network branch itself by mixing return with the hot supply temperature. So that's at this point 1 there. So there we can control the temperature of the water going into this pipe network. Then we have the substation in the multifamily house, and there we were able to control the set point of the supply water going into the heating system. So there's 2 controlled variables. We can control the temperature of the water going into the network, and we can also control the temperature of the water going into the indoor heating circuit of this apartment building. And how it's done is actually we override the typical heating curve control set point. So it's very easy to do actually. What we did in this case study was we tested for a few weeks, we tested a few cases. So what we wanted to achieve was see to what extent we could use the building to shave off the peak consumption in the network. Yeah? We can charge and discharge the building, and as such, you can lower the peak consumption. That was the idea. We did it for 2 different setups. One is what we call non-mixing mode, which means that the mixing station is not active. We just have the high temperature of the main Brescia heating grid then. And we did it also when the mixing mode or the mixing station was active. And then we also, as a second kind of test, we also tried to manipulate the supply temperature going into the network itself to see in what extent we could use the network pipe system as a storage. And indeed, as explained, the objective was to reduce the peak heat load because that's typically very expensive and typically produced by fossil fueled boilers. So you want to minimize this peak load as much as possible. So we just calculated the energy above our threshold for these 3 cases. So what you see here is the control signals for 10 days, 11 days. So this is the output of the controller. And if this value is positive, it actually says to the building that it's hotter out or warmer outside than it actually is. And the building controller will, or at least that was the idea, that the building controller would reduce its energy consumption because it thought it's not needed anyway. If it's negative, it would say it's actually colder outside than what is the case. And as such, the building would consume more than it actually would in benchmark situation. So these are the control signals, and they make pretty much sense because typically you have a power peak in the morning, and you would have a power peak around 5 o'clock, 6 o'clock when people come back home, switch on their heating. So the control signals have a positive offset at exactly that moment, trying to scale down the energy consumption. But on the bottom, you see the effect on the heat load, and actually there was very little impact on the heat load profile. And in a few slides, I will come back to what we think the reason for this is. Yeah, this gives you just the same conclusions, but then in another graph. So in non-mixing mode, that was at very cold temperatures or very at cold outside weather. You see that there's actually very little impact benchmark compared to test data. And also in a mixing case, it was like this. So then the second case study, where we want to use the network as an energy storage system. Also here you see the control signals, which are very sensible, you could say, because what it tries to do is before the peak heat load would come, let's say at 6 or 7 in the morning, it so you see a drop, which means that the controller is telling the system that it's colder outside, so it would pre-charge the network. It would increase the temperature going into the network in anticipation of this peak, and as such, when the peak is there, the peak would be lower. So the control signals made sense in our opinion, but again, we have very little impact on the heat load profile. So actually, it's not what we had hoped for. So before going into the discussion of why we think this happens, one of the remarks that we have to make is that the heat load profile is very sensible, not only to the weather, but also to a lot of other external disturbances. For example, domestic hot water consumption, occupancy in the building. And therefore, it's very hard to say what the building would have done if the smart control was not active. So we had to normalize the benchmark data to filter these results out. And this means that you need a lot of data actually to be able to construct a benchmark profile. And we didn't have that much benchmark or data available. So that is one of the reasons actually what makes it hard. And then some other reasons why we think the tests at that time were not going that well. First of all, when the weather is rather warm, the peak load is already very low in this network. So the controller can't add much, cannot bring much extra. But more importantly, during cold weather, what we noticed was that actually the substation didn't reach its set point. So that's this graph with the blue, so the blue dots. That's the actual that's the actual measurement of the supply temperature going into the heating circuit. While this black line is the set point, and you see that in these cold periods that the substation cannot reach its set point, and because it doesn't reach its set point, if you play a bit with the set point, it doesn't make much of a difference. And we did not account for this effect in the modeling of our substation. So that is something that we learned looking into the data. Another thing is that the network itself was very small, so the capacity, the thermal capacity is low. This also means that you cannot store much heat anyway in the setup that we had. So that brings me to the conclusions. What we did was we developed this supervisory control system. We implemented it in the Brescia network. We did tests beginning of this year. After the tests, with all the conclusions that we, with the things that we saw, that the impact is not so high. Obviously, we learned from this. So what we did in the previous months was that we are now testing again with an improved control algorithm, we hope, taking into account all those things that we came up with. And we also worked with longer test data. So we hope that by next edition in 2024, that we can give you some better results. It's just to say that there's so much difference between simulating things, and everything works in theory, and then you put it in practice, and then you bump into all kind of different issues. But anyway, that's life. Thank you. That's what I wanted to say.
Thanks a lot, Dirk, and thanks a lot for the nice presentation. So questions, Eric?
Yeah, thank you very much for a very nice presentation. I have a question related to the network model, the thermal network model. You said, correct me if I'm wrong, but you used a regression type of models.
Yes.
Was this a linear model or non-linear model?
We used, in this case, linear regression. So indeed, there's already an error in the modeling itself.
Yeah, because I think there is a strong non-linearity between flow and temperature.
Yes, that's definitely the case. But in when you do optimization, the models that you use, it can't be too complicated because you run into computational problems then. But indeed, we know that there's
yeah, because you can vary the flow and the temperature independently,
Yes.
more or less, and then you need to take the non-linearities into account, I think.
We're aware of that, indeed.
Yeah. That's good. Thanks again.
Actually, we formulated now a new PhD, which will start next year, especially on this non-linearities.
Yeah, we can let's talk about this there.
Yes.
More question? Yes?
Thank you. I had a question with the buildings. I mean, you instead of turning off the supply like we saw in the lean heat approach, you manipulate with the sensor input instead, or impersonate the outdoor temperature by increasing or lowering. But for how long do you do it? I mean, so I assume you do it like on an individual building basis, right?
Yes.
But how do you know for how long you can, manipulate the temperature sensor for one building management system, since the heat loss from the individual buildings are very different?
Yeah. Here you touch a very sensitive topic, because if we go to potential customers, they always say you're screwing up my thermal comfort if you give me not enough heat. So it's difficult discussions always. The control signals that we send are like periods of 15 minutes to maximum an hour. And also typically we would install indoor sensors, not for the control itself, but to guarantee or to show to the people that there's nothing happening to their indoor comfort. So, but that is indeed one of the things you always have with this demand response in buildings, that you have to guarantee that comfort is not violated.
Yeah, because we see with some of the older buildings that you can lose like 1 degree in an hour.
Yes.
So if you took it for an hour or 2 hours, right, then people will start to complain.
Indeed, the 2 hours, that's more for heavy buildings, well insulated, where you don't see much effect. Indeed, for the older buildings, it's not recommended.
There is another question on the back.
Yes, thank you for the very interesting presentation. When we analyzed flexibility from the piping water and from the thermal mass of buildings in admittedly way less operational detail, we could often see that depending on the size of central heat storage, that the effect of the flexibility, this indirect flexibility, might get eaten up by heat storage, because it's so cheap, and a lot of systems just have a massive amount of central heat storage. Did you get any perspective on that?
Yeah, well, few years back, we also had a PhD student working on exactly how large the thermal capacity of the piping network is compared to centralized heat storages. And indeed, one of the conclusions there was that it makes sense, but only for quite large networks. So definitely not this branch of a few hundred meters. There you cannot store too much heat, and then indeed you need to go to a centralized storage system. But in large networks, like the bigger network, like Vienna, for example, very large city networks, there I think there's a potential in using the network as a storage itself. Not in this.
Thank you.
Welcome.
Yes, Etienne.
Yeah, thank you for the presentation. It was really interesting. I was just wondering about the building model accuracy. Like, did you see a lot of variety in terms of performance from one apartment to another, or is it something that's like you see that the thermal behavior is kind of the same for each
Well,
room?
here the entire apartment building was modeled as being as a one zone model. So it's
Oh, okay.
also
That's
there you have a
aggregated
lot of
loads. Okay.
yeah.
I see. And for you consider like two capacitances. It's second order RSC model. So I was just wondering, like, have you made any comparison with the data to see if it's kind of like fits the data?
Yeah, well, these building models, that is something that another department or unit in our department develops. They are the experts there, so we just used what they have developed without validation of these things. That's their task, and we just we just trusted that what we got was the best they have.